Hi, I'm Ishrad Jahan. Today I will be discussing my solutions for DataSynthis round 2, where I am covering some key concepts of data structure and algorithm. Outlines of this presentation: minimum spanning tree, segment tree or Fenwick tree for ransom queries, Splay trees, and connected components on social graph. First of all, I talk about minimum spanning tree. Imagine we need to connect several houses to a central office using telephone wires. The simplest idea would be to connect every house directly to the central office. Where this might work, but it's a naive approach and very expensive. So we need a smarter way to minimize cost. So what will be the better approach? Instead of connecting every house individually, we can connect them in a network where some houses share connections, as long as there's still a path from every house to the central office. Everyone stay connected, and this approach minimizes the total length of wire needed, also reducing cost without losing connectivity. This idea leads to an important concept in graph theory called the minimum spanning tree. So what is minimum spanning tree? A minimum spanning tree or MST is a subgraph or weighted undirected graph. It connects all the vertices together with the minimum possible total edge weight, and importantly, it has no cycles, meaning it's a tree. In our example, the houses and the central office are vertices and the wires are edges with certain length or cost. The MST help us to find the cheapest way to connect everything together efficiently. There are several minimum spanning tree algorithms. Let's look at one of the most popular ways to build it, Prim's algorithm. Let's see how it works visually. We start from one node. For example, here we start from E. Then we pick the smallest edge connected to it. Here the smallest edge connected to E is DE, and add that new vertex to our tree. New vertex is D. So now we add D to our new tree. So D is added. From all the edges connected to the growing tree, we again pick the smallest one that leads to the vertex we haven't added yet. So here this vertex is the smallest vertex which connect A, which have not added to our tree yet. So pick A to our tree. Repeat this procedure and finally we got our minimum spanning tree where the edges are taken DC, BE. So here we see from our final minimum spanning tree there have 5 vertex and 4 edges, which follows the rules of tree. If a tree have n number of nodes, there must have n minus 1 number of edges. So this is our final minimum spanning tree. What will be the complexity of Prim's algorithm? Time complexity. With a simple adjacency matrix, it runs in order of v squared time. But with a priority queue or min heap, it can be reduced to order of E log v time, where v is the number of vertices and E is the number of edges in the graph. Applications of minimum spanning tree in machine learning. Any graph visiting at minimum cost, minimum spanning tree can be used. And one of the most used sector is image segmentation. Minimum spanning tree based algorithm can be used for image segmentation by treating pixels as nodes in a graph and edge weights as a measure of dissimilarity between adjacent pixels. The minimum spanning tree can be used to identify boundaries and segments in the image. Prim's algorithm is widely used in network design problems such as connecting cities, laying cables, or even clustering in data science. Now, while we're talking about segment trees, a powerful data structure widely used in range query problems. Let's start with the basics. So, what are segment trees and why do we need them? A segment tree is a type of binary tree that helps us efficiently answer range queries over an array, such as finding the sum, minimum, or maximum between two indices. Normally, a simple approach would be take order of n time per query, but with a segment tree, we can do it just order of log n time. Not only that, segment trees also allow updating array elements efficiently, again order of log n time. This makes them perfect for dynamic data structure where values changes frequently. There are three main operations in segment trees. Construct, which build the tree from the array. Update, modify an element or range. Query, get information from a range like sum, minimum, or maximum. Now let's see how we can construct a segment tree. We have an array A equal to 1, 3, minus 2, 8, minus 7. The goal is to build a tree where each node stores the sum of a segment of this array. We use the function build where it takes node left, right, and array, where L and R are the left and right boundaries of the current segment and T denotes as the tree. If left equal to right, it means we have only one element, that's leaf node. So we simply store the element tree of node equal to array of left. Otherwise, we recursively build the left and right parts by computing mid equal to left plus right divided by 2. On left side, we call from left to mid, and on right side, we called mid plus 1 to right. Finally, we combine both result into tree of node equal to left part and right part by summing. Let's go through the example quickly. Left part 0 to 2 gives the sum 2 and right part 3 to 4 gives the sum 1. So the root node stores 3, the sum of the entire array. In this way, the whole segment tree is built in order of n time using recursion. Now let's see how we update a segment tree using this algorithm. The function which takes the parameter as where capital L and R means is the current segment and small l and r is the update range. On first step, if the segment is out of range, that means we simply returns since there is nothing to update. If left equal to right, that means we are at the leaf node and so we directly set tree of node equal to value and return. Otherwise, we will recursively update. Same as building tree, we firstly find the middle point and update from left to right. After both are done, we recalculate the parent node. For example, suppose our array is 1, 3, minus 2, 8, minus 7, and we want to update the range from 1 to 3 with value 2. This function skips segments that are outside of 1 to 3. For segments that overlap, it goes down until it reaches the leaves within 1 tree and sets them to 2. Then, on the way back up, it recomputes the parent sum. The updated array becomes 1, 2, 2, 2, minus 7. And the segment tree nodes now reflect these changes. Let's see how we query a segment tree. The query function checks if there is overlap or not. If there is no overlap, that means the segment is out of range. If the current segment is completely outside the query range, we simply return 0 because it doesn't contribute the answer. Second case is complete overlap. In case of complete overlap, that means the portion entirely inside the query range. In that case, we return tree of node because the segment's sum is fully part of our answer. Lastly, another case is partial overlap. In that case, we simply divide our tree to find left sum and right sum. After recursively call, finally we add the left sum and right sum and then return. Here is an example where we went to find out the sum from index 2 to 4, which is minus 1. In that case, the tree skips parts that are outside 2 to 4. It only adds the segment that overlap the range. So the answer would be minus 2, 8 and minus 7, which is minus 1. The segment tree quickly finds this in order of log n time because it doesn't need to check every element. Next is Splay Trees. In large-scale ML systems, multiple models may serve predictions concurrently. Efficient model caching is critical to minimize loading time and memory overhead. Our goal is to optimize cache access pattern to reduce average prediction latency. So there is another available tree other than AVL tree or red-black tree. So I quickly share you an example that why it is better than AVL or red-black tree. You know that both AVL and red-black are self-balancing binary search tree and outperform so many data structures. But Splay there is a king of particular scenario. Splay tree is actually equal to AVL tree or red-black tree, meaning this is also self-balancing tree. We all know that binary search tree have three operations: insertion, search, deletion. But Splay tree does one thing extra. When we insert the data, just after that, it does splaying. When it searches for some data, it does splaying, and also after deleting some data, it also does that. Meaning, after each and every operation, it does splaying. Now talk about what is splaying. Splaying is an operation to bring all the most frequently used element closer to the root. So if I say I went to search 12, 14 and 16, my binary tree look like this, where 14 will be the root and 12 will be the left child and 16 will be the right child. Let's say if I went to search 16 again, I don't like to go to here to here and also here to here. Here I need 3 comparison, but using Splay tree I need only 2 comparison. And you know what? Once I search 16, 16 will become to the root here. Here the whole tree arranges some order. I am not going to discuss that, but just notice that if I search 16 again, it is actually the root. The whole idea is what your search operation is doing. The possibility is that it has a repeated job and Splaying optimize the searching time. And this is a kind of caching mechanism, and it is keeping the most used data towards the root. So that is don't have to go again and again to the bottom. Here I see that how rotate the tree. This is an example of jig and zag rotation, where jig rotation rotates the whole tree in single one unit to left, and here the tree is rotated one unit to right. How it optimizes ML model cache. In a production ML system, we often serve many models, for example, user personalized models or feature specific models. Some models are accessed repeatedly, while others are used rarely. By storing models in a splay tree, frequently accessed models automatically move closer to the root. This reduces lookup time for popular models and minimizes repeated loading from disk to memory, thus optimizing prediction latency. What are the trade-offs compared to LRU cache? Splay tree is self-adjust dynamically, where LRU cache uses queue or map for tracking. Since LRU cache uses queue or map for tracking, it takes order of 1 average time for memory access. It's simpler, fixed size and eviction, but Splay tree is more complex as it rotates on every operation. LRU cache predictable cache capacity, but Splay tree frequent reuse of few models. While an LRU cache explicitly removes old entity, a split tree adapts naturally based on access frequency. No need for external eviction logic. When splaying harm latency. However, splaying is always ideal if the access pattern is uniform or random, meaning models are accessed unpredictability. Then every access triggers unnecessary tree rotations. These rotations increase CPU cost and can slow down prediction serving instead of helping it. So, split trees work best when there's temporal locality. When certain models are reused frequently within short intervals. To summarize, splay trees improve ML cache efficiency by adapting to dynamic access pattern. They bring frequently used models closer to the root, reducing lookup time. Compared to LRU caches, they are more adaptive but can be slower under random workloads. The right choice depends on access locality and system workload characteristics. Next, disjoint set operation, also known as DSU or union find. We start with several separate elements, each treated as an individual set. A disjoint set supports three main operations. These are make set, union, and find set. The goal is to efficiently group elements and determine which group a particular element belongs to. Understanding disjoint sets. Here we can see how elements are grouped. Initially, all elements are in one pool, separate from each other. After applying union operations, they form smaller groups or clusters based on their relationships. Each color here represents a distinct set or connected component. Three operations are make set, union, and find discussed here. Let's understand these operations. Make set, where every element starts in its own set. Union operation combines two sets into one. Find operation finds the representative or parent of each set containing X. So, if two elements have the same representative, they belong to the same group. This is especially useful in graph problems like finding connected components or detecting cycles. Here in this example, we see that there have two connected components and 1 and 5 are the representative of each group. If we apply find of 2 or find of 3, find of 0 or find of 1, in 4 cases it returns 1. And also in the graph which is right sided, if we apply find of 4 or find of 5, it returns 5. How to implement this? Here's how we implement these operations. Each element has a parent pointer. Initially, each node is its own parent. The find function traverses parent links until it finds the root element. That's the set representative. The union function merges two sets by making one root the parent of the other. In this example, we perform union of 0, 4. So both 0 and 4 end up in the same set. Using DSU, we can easily find connected components in a graph. For each vertex, we find its ultimate parent using the find operation. Then we collect all unique parents that tell us how many connected components the graph has. In this example, nodes 0, 1, 2, 3 are connected while 4, 5 form a separate component. So here the number of connected components is 2. To optimize the DSU, we use union by rank and path compression. Path compression flattens the tree whenever we call find, so future lookups are faster. Union by rank ensures that we attach the smaller tree under the larger one to keep the structure shallow. Together, these optimizations make both operations nearly constant time, which is from order of n time to order of log n time. Basically, each node has three properties. These are rank, data, and parent. On find set operation, the path is compressed, and on union operation, we use rank. Let's see an example step by step. We start by creating 6 separate sets using make sets, where each node considered as an individual set. Then we perform a few unions. For example, union of 1, 2 and union of 4, 5. When I apply union of 1, 2, since both have rank equal, it doesn't matter which will be the root node or which will be the leaf node. Here I make the parent of 1 equal to 2 and also parent of 4 equal to 5. Since 2 have a child node, its rank is increased by 1. So here 2 and 5 both increased rank by 1. After that, union 1, 3 connects 1, 2 and 3, while union 5, 6 connects 4, 5 and 6. Here we can see the parent and rank updates at each step in the table. Next, union of 4, 3 merges the two groups into a single connected component. Then we perform some find operation. Find of 4 links 4 directly to its parent, and then apply find of 3, which directly connected with roots. So there is no path compression, and then again apply find of 6, which connects 6 with 2, and path compression is applied. At the end, all nodes are efficiently connected under one representative using path compression. So, to summarize, disjoint set union is a powerful data structure for grouping elements efficiently. Using this make set, union, and find, Along with optimizations like rank and path completion, we achieve near constant time per. It's widely used in problems like finding connected components, Kruskal's minimum spanning tree algorithm, and cycle detection in graphs. That's all. Thank you for watching.